Hi, this is Dave Johnson with another edition of Math Off Topics. In the last video that I did in this series, I talked about the fact that the expression for E is monotonically increasing. And in this video, I'm going to show that the expression is bounded above. In other words, it has an upper bound. And given those two conclusions, that the expression is monotonically increasing and that it's bounded above, one can use a theorem from real analysis. You may have even seen this theorem in your textbook talking about limits. Then you can say that the limit of that expression exists. And what we're trying to do here is show that E exists. So let's get into it. So this is the same expression that I used in the other video, 1 plus 1 over p raised to the p. This time we're trying to show that it's bounded above. And I'm going to take a similar approach, although once we get about halfway through, we'll see it's very different. But again, as I said before, I don't want to use the binomial theorem. I want to use the generalized binomial theorem. And so let me write that. 1 plus x, and I'm going to raise it to the p power, and that's equal to 1 plus px plus 1/2 p times p minus 1 x squared plus 1 over 3 factorial p times p minus 1 times p minus 2 x cubed plus dot dot dot. So there's an infinite number of terms. In this one, we're going to try to get, we're going to rewrite this series using inequalities to show that we can find an upper bound. And so let's go ahead and replace the x with 1 over p. So we get 1 plus 1 over p raised to the p is equal to 1 plus, now the p times x is going to become p times 1 over p, which is another 1, plus 1/2 p times p minus 1 times, and now the x gets replaced with 1 over p, so we get 1 over p squared plus 1 over 3 factorial p times p minus 1 times p minus 2. X cubed gets replaced with 1 over p cubed plus dot dot dot. Okay. And again, we have, so like in this case here, we have p factors in the denominator. So we have 1, 2, 3 factors here. And for each term, we're going to have as many factors downstairs of p as we do these factors upstairs. So I can go ahead and say, just divide each of those factors by the p. So we get, let me simplify, so we get 1 plus 1 over p raised to the p is equal to 1 plus 1 plus 1/2. Now p divided by p is 1, but then we get 1 minus 1 over p plus, and then 1 over 3 factorial. The p again goes away because p divided by p is 1, and we have a 1 minus 1 over p times 1 minus 2 over p, and we can see that this keeps going like that. Okay. Now, this is where we're going to start replacing things with inequalities. And we have to be careful when we do this. So p is greater than probably should say that here, p is greater than 1. And in particular, p is greater than 0, but we already knew that. And so this factor, or this term, is going to be less than or equal to 1/2. And this factor is going to be less than or equal to 1 over 3 factorial. And really, I could write this as 1 over 2 factorial. So let me clean that up just a bit. And if we keep going, we would get less than 1 over k factorial. Okay. Why is that? Well, because p is greater than 1, this is going to be less than 1, and 1 minus something that's less than 1 is still going to be greater than 0, but it's going to be smaller. And when you multiply that, you get something which ends up being smaller. So this is smaller than this. Likewise, this is smaller than this, and that's going to be true for every term. So I can replace this with writing it this way. So 1 plus 1 over p raised to the p is less than or equal to 1 plus 1 plus 1 over 2 factorial plus 1 over 3 factorial plus ... Now, I think we know where this is going. I could write plus 1 over 4 factorial plus 1 over 5 factorial, but what I want to do instead is write this as a summation from k equal 4 to infinity of 1 over k factorial. And notice it's an inequality. We're saying that all of this is bigger than this. So if we can calculate what this is, or even get an approximation to this, which is still bigger, then we will have an upper bound on this expression. So that's kind of where we're headed. Now, I do want to say, but hold on there a minute, 1 over k factorial is less than or equal to 1 over 2 raised to the k for k greater than or equal to 4. Now, I've seen proofs out there, and when I say out there, I mean out on the internet or in textbooks. Yeah, you got to be careful. This is only true as long as k is greater than or equal to 4. It's not true, as I've seen some places say, k is greater than 2 or something like that, because it's not true. So I can replace this 1 over k factorial, because it's k greater than or equal to 4, I can replace that with 1 over 2 raised to the k. Let me go ahead and do that. So 1 plus 1 over p raised to the p is less than or equal to 1 plus 1 plus 1 over 2 factorial plus 1 over 3 factorial plus the summation k equals 4 to infinity of 1 over 2 to the k. So this inequality is still true, but now we've got a 1 over 2 to the k. The nice thing about that is it's a geometric series, and we can sum that. And so let's go ahead and do that. But I'm going to do a little trick here. So let me start the sum from 0. So this is going to be k equals 0 to infinity of 1 over 2 to the k. Now we're only interested in this part of it here. Okay. So let's expand the 0th, 1st, 2nd, and 3rd terms. So if k is 0, we get 1. If k is 1, we get 1/2. If k is 2, we get 1/4. And if k is 3, we get 1/8. and then plus our summation, k equals 4 to infinity of 1 over 2 to the k. But we know how to sum that expression, and you might want to go back and look at your the geometric series, an infinite geometric series. So we get 1 divided by 1 minus 1/2, because 1/2 is what is called the common ratio. And so if we do this arithmetic, we get 2. And so this is equal to 2. And now we can calculate what summation k equals 4 to infinity of 1 over 2 to the k is. That's this minus these terms. So 2 minus the quantity 1 plus 1/2 plus 1/4 plus 1/8. And let me just hold on to that. We're going to plug this back in to our expression here. So 1 plus 1 over p raised to the p is less than or equal to 1 plus 1 plus 1 over 2 factorial, which 2 factorial is 2, so 1/2, plus 3 factorial is 6, so plus 1 over 6, plus, and now what we got for this, which is 2 minus 1 plus 1/2 plus 1/4 plus 1/8. And if we sum all of those and simplify, we get the result that 1 plus 1 over p raised to the p is less than, and I've done the arithmetic here, it's 2.79166, and that 66 repeats. Okay. Now, what have we just shown? Well, we've shown that this expression cannot be any bigger than this number. Now, this isn't the value of e. In fact, e is smaller, which is kind of a sanity check on our work. But we have proven that this expression is bounded above, and that's what we set out to prove. And when you combine that bounded above with monotonically increasing, so monotonically increasing means that it's always increasing. When you combine those two facts together, you get that the limit for e exists. And so we have proven, therefore, rewrite it, therefore e exists. I hope you've enjoyed this video. If so, please like and subscribe, and I will see you in the next video.